Hi everyone, today's video is about asymmetric cryptography, public keys, and encryption and decryption. So the idea of using a public key was first introduced at Stanford University in 1976. Unlike cryptography with a symmetric key, encryption with a public key is a relatively new concept. Symmetric cryptography is equally suited to large financial corporations that use secret information transfer. With the proliferation of unprotected computer networks over the last few decades, there was an urgent need to use cryptography on a wider scale. The symmetric key is impractical because of the problems it faces when managing the system. It has resulted in encryption with a public key. To understand the principle of asymmetric encryption, you should always remember that you are dealing with two keys. The encryption begins with public key publication that can be made, for example, via the server or by email. The user does not have to pass it on a secure path, so everyone can take the public key. It is often desirable to spread it globally to ensure there is no other fake public key. By using a public key encryption system, anyone can encrypt the public key owner information. Therefore, the message is decrypted by the secret key of the recipient. That's why it's so important that the key remains secret. Its owner can decrypt all messages encoded by others that own public key. Such crypto systems are used to encrypt data from public keys, authentication, and integrity. Known examples based on asymmetric methods are OpenPGP, as well as cryptographic protocols such as SSH, SSL, TLS, and even HTTPS based on asymmetric crypto systems. The advantages are relatively high safety. Also, you don't need as many keys as in the symmetric encryption method. There is no problem with switching keys, and you have the opportunity to authenticate with digital signatures. The disadvantages of public key encryption systems are that algorithms work very slowly, approximately 10,000 times slower than symmetric. Also, you need to use long key length because it is required. There is multi-user issues as well when the message needs to be further encrypted. And for each public key there is a security risk, which is a disadvantage of public key encryption systems. So the public key encryption is also known as PKE, asymmetric encryption, asymmetric cryptography, asymmetric cipher, and asymmetric encryption of the encryption keys of Diffie-Hellman. So the PKE is a cryptographic algorithm and a cryptosystem component implemented by various internet standards, including TLS, PGP, GNU, SSL, and HTTP. Public key encryption provides a secure connection through a malicious channel, which allows you to read messages only from the destination recipient. Public key encryption is also a DSA component that is used to authenticate a secret key that can be verified by any person with legitimate access to public keys. Thus, public key encryption facilitates the confidentiality, data integrity, and authentication that form key information parameters. Public key encryption is slower than cryptographic secret key methods or symmetric cryptography due to high computing requirements. This is a clear lack of open source encryption systems. Unlike symmetric cryptography, the public key encryption uses a fixed buffer size, depending on specific and small volumes of data that can be encrypted and not threaded. Because a wide range of possible encryption keys is used, the public key encryption is more reliable and less susceptible to attempts of security breach. Different keys are used for encryption and decryption in the public key encryption. This is a property that sets a scheme other than symmetric encryption. Each receiver has a unique decryption key, usually called closed. The recipient must publish the one that is called the public key of the encryption method. This scheme requires some confidence in its authenticity to avoid replacing the attacker as a recipient. Typically, this type of cryptosystem includes a reliable third party that indicates that a particular public key belongs to a particular person or object. The RSA public key encryption algorithm is rather complicated to prevent open encryption, text encryption, and public key encryption keys being displayed. Any person or party wishing to connect to cryptography generates several capabilities at the same time, namely an open and encrypted encryption key. Furthermore, the encryption and decryption process is relatively simple and easy to compute. Interestingly, RSA does not work directly with bit lanes, as in the case of a symmetric method. It works with modules n. It is therefore necessary to provide open text as a series of numbers smaller than n. So, the security of the RSA depends on the strengths of the two separate functions. The RSA cryptosystem is the most popular public key cryptosystem based on the practical complexity of factorizing large numbers. The encryption feature is considered a one-way function for converting open text into encrypted text and can only be undone by using a secret D key. The complexity of determining an open and closed RSA encryption key is equivalent to the modulating factor of the n module. Thus, the attacker cannot use the RSA public key knowledge to determine the secret RSA key unless he can determine n. This is also a one-way function. The transition from the values of P and Q to module n is easy, but opposite is not possible. If either of these functions is not one-sided, RSA is violated. In fact, if factoring technology is effectively developed, RSA will no longer be safe. The strength of RSA encryption sharply decreases against attacks if the numbers P and Q are not prime numbers of the selected public key E is a small number. Along with RSA, There are the cryptosystems with public keys. Many of them are based on different versions of the problem of discrete logarithms. The ElGamal cryptosystem, called the Elliptic-curve variant, is also based on the problem of discrete logarithm. It gains the power of protection by the fact that discrete logarithms cannot be found in a practical time interval for a given number, whereas the effect of reverse power can be calculated efficiently. So, for example, a simple version of ElGamal that works with numbers from modulo P. In the case of elliptic-curve variants, the method is based on completely different calculation systems. Each user of the ElGamal cryptosystem generates a pair of keys. The elliptic-curve cryptography is a term used to describe a set of cryptographic tools and protocols whose security is based on special versions of the discrete logarithm problem. It does not use the numbers on module P. The ECC is based on groups of numbers associated with mathematical objects called elliptic curves. There are rules for adding and calculating a plurality of these numbers, as well as for the numbers per module P. The ECC includes variations of many cryptographic schemes that were originally developed for modular numbers, such as ElGamal encryption, public key encryption algorithms, and digital signatures. It is believed that the problem of discrete logarithms is much more complex with respect to the points of the elliptic curve. This leads to the transition from the numbers P to the points of the elliptic curve. An equal level of security can also be obtained with shorter keys when elliptical curves are used. Shorter keys lead to two advantages of encryption of public key information. The first one is easy key management, and the second one is effective calculation. These advantages make empirical encryption schemes very attractive for applications with limited computing resources. You can quickly compare RSA and ElGamal schemas in different ways. Now let's talk about SSL, or Secured Socket Layer Protocol. The Internet traffic that transmits information via interpolation computers can be intercepted by a third party. So the first method is eavesdropping. The information remains unaffected, but its confidentiality is compromised. For example, someone can collect credit card numbers, record confidential conversations, or keep sensitive information. The second method is counterfeiting. The route of the information is changed or replaced and then sent to the recipient. For example, someone can change the order of goods or change a person's autobiography. The third one is personification. The information is provided to the person who represents the recipient. The personification can take two forms: replace. So one can pretend to be someone else, or distortion. A person or organization can distort themselves. For example, a site may qualify as an online furniture store when it actually receives credit card payments but never sends any items. Public key cryptography provides protection against internet attacks. It is not appropriate to calculate a private key based on a public key. Therefore, public keys can be freely used, allowing easy and convenient use of encryption of content, and digital signature verification, and secret keys can be kept secret by ensuring that only private key owners can decrypt content and create digital signatures. Since public keys need to be separated, but they are too large to be easily stored, digital certificates are used to store them for safe transport and sharing. Private keys are not used together. They are stored simply in the software or operating system used, or in hardware such as USB flash drives, or hardware that contains drivers that allow it to be used with software or operating system. Digital certificates are issued by organizations known as certification centers. The key business applications for public key cryptography are digital signatures, where the content of a digital signature with a private key is checked by the public key of the user. The second one is encryption. Here the content is encrypted with a public key and can be decrypted only with the user's private key. Assuming a private key is not compromised, encryption of data and messaging provides the following security benefits. The first benefit is privacy, because the content is encrypted with the user's public key. It can be decrypted using a private key to ensure that only the intended recipient can decipher and review the content. The second benefit is the integrity. Part of the decryption process includes checking whether the contents of the original encrypted message and the new decoded match, so that even the smallest change in the output will result in a process failure. Public key infrastructure is a background cybersecurity and event that is described as a set of policies and procedures needed to create, manage, distribute, use, store, and recall digital certificates. PKI, based on asymmetric cryptography today, is widely used to provide online messaging for online purchases, also internet banking and email, as well as to protect communications between millions of users and the websites they connect before using HTTPS. Although it is easy to encrypt messages without public key infrastructure, the user cannot easily check who they are communicating with. In other words, public key infrastructure helps the user to verify or confirm the person with whom they are communicating. A typical public key infrastructure ecosystem includes the following key components. Certification policy is a security specification that defines the structure and hierarchy of the public key infrastructure ecosystem, as well as policies related to key management, safe storage, processing, and cancellation. The second component is the root certification authority that is responsible for authenticating the system. Next, the intermediate certification authority is certified by root CA for specific purposes defined by the certificate policy. Digital certificates are usually issued and signed by certification centers. The certificate database stores their records. Cancellation service is a server that publicates revised CRLs or an online certificate status protocol that use CRL and responds to revocation checks for devices that cannot handle the CRLs themselves. Asymmetric cryptosystems are thus used for encryption, authentication, and integrity. If the striker does not have a public key, encryption key, he will never be able to use a secret data. Well-known examples based on asymmetric methods are OpenPGP, but cryptographic protocols like SSH, SSL, TLS, or even HTTPS are based on asymmetric cryptosystems. So, thank you for watching. This is for today's video. I hope you enjoyed it. See you next time. Bye bye.